Hello everyone. In this video, I will show you how we can use PCA to decompress a photo. So what we will do first, I have here a document, an R document, that I'm going to save. So I save my document and I will pick the location and I take the location where I put the photo that I want to use. So for me, it's in the part 2 folder PCA and then a subfolder R code. And if you look in this folder, we have here Quentin Juno, which is a photo. So that's the photo that I will use. So I call this file photo R, for example. Then I set my working directory as the same as the file location. And in that case, R can find back the photo. So let me first download or load the library JPEG, because that's a library where we can find the function read JPEG to import the photo, the JPEG picture, into R. So we start with reading the picture. And if we look at the picture, it is an object with 3 dimensions. We have a length and a width, say, and then we have three different matrices that have these dimensions. And for example, we can determine R, and we can, for example, look at what is in R, and you see R is a matrix. And for example, I can look at the first element in R, it is this value. Or I can look at the first 10 elements, and you see here all the values. The same holds for G and for B. So what are these values? For example, I can look at R11, G11, B11. If I represent my original picture and I subdivide it in smaller rectangles, then this is the first rectangle, say, the rectangle 1, 1. And in order to determine the color that this rectangle has, I need a number for R, I need a number for G, and a number for B. So with this information, we know what is the color of the first pixel of the photo. And then if I do dim.picture, for example, I see that this is a dimension, the resolution of my picture. The more pixels I have, the finer, the more detailed the photo can be. So we represent a picture as a collection of pixels, where each pixel is represented by an R, a G, and a B value. Okay, if I take R, R is a matrix with this many rows and this many columns. And what we assume is that each row is an observation. So we have 1359 observations for R. And each observation consists of this number of variables. Say we have x1, x2, x3 until x 1179. So then R, this R here, you can think of it as a data set. A data set where we have the observations divided over different rows, and each column is one variable I have for each observation. What we do is we will make a scatter plot of 2 different columns. For example, let's make a plot of column 10 and column 11 of the R matrix. Of course, you can do the same for G and B. And here you see the plot. And what we see is that the 10th and the 11th column are very strongly dependent, which of course makes sense because these are two columns in your picture which are very close to each other, and you do not expect colors to change very rapidly if you move from the left to the right in the picture. However, if we plot, for example, column 10 and I say 20, for example, we see still a positive dependence because the columns are not too far away, but it's not that strong as 10 and 11. And if we take, for example, here 200, you see that there is now not any very strong dependence, which again makes sense because the pixels in column 10 are far away from the pixels in column 200, so well, these colors can be very different, and therefore you find this plot. So let's just make a figure where we put 4 plots together to see the difference in dependence between columns of R. So I take here a figure with 4 plots, 2 on top and 2 on the bottom. That's why I have MF row C to 2. And here you see the plot, a very strong dependence here and here if we take columns which are close to each other, and then you see the weaker or the almost independence when we take the columns further away from each other. What we will do is we will apply PCA on each of the matrix R, G, and B. So we do 3 times a PCA analysis. And this takes a while to run because R is a very large matrix. So it takes a while to do the PCA analysis, and then you have to do it again for G and for B. So at this point, we have to wait a little bit. We can, for example, have a look at R.PCA. We see that we have many principal components. So we have more than 1000 principal components, of course. You see here the number of principal components that we have, and we see here the different standard deviations, where again, the first principal component has the highest standard deviation, and then you see that it decreases over the principal components. What we see here is that there is a large standard deviation for the first principal components, but that goes down very quickly, and at the end you have principal components with a very small variance. So the question is now, how many principal components do I need to keep in order to still be able to restore the original picture? So what we do is we will determine a certain number of principal components, say k principal components. It means that if you have k principal components, we have the z1, z2 until zk value of the PCA analysis. And then we will move back from the z values to the x values by only using the k, the first k principal components. And remember from the lecture that if we have all the principal components, so assume that we use all the principal components 11,179, then we have z1, z2, z3 until z1179 for each observation. Then we can use all the principal components and the z values to restore the full picture, meaning there is no information lost. However, if you only have k principal components, we cannot exactly replicate the picture, but only in approximation. And the question is this approximation good enough? So for that, I'm going to write a function, and I call this function extract, because this function starts from M, which is a PCA object. So for example, this could be R dot PCA. And what this function is doing, it starts from the information in M of the PCA analysis, then uses the Z values, so these are in MX, but I can only use the first K components. So in $X are the transformed, the Z values of your data over the different rows. Each column represents of a principal component, and therefore I say I can only use the first K principal components. And I have to multiply this with the rotation matrix. So M $rotation. This is your rotation matrix. And again, I can only use the first K principal components. So in the columns of M $rotation are the principal components. So the first row is the first principal component, the first column is the first principal component, then the second principal component, and so on. So I use a rotation matrix, but only made up of the first K principal components. And I need to take the inverse of the rotation matrix, but that's the same as the transpose. So this is my Y that I will return. So what I have now is I have a function extract such that I can plug in my PCA analysis and say, well, restore the data if I can only use K principal components. So for example, we can say, well, I'm going to restore my picture when I use only 5, 10, 100 or 500 principal components. So for that, I'm going to use the sApply function, because in the sApply function, I can say, well, use the sApply function on this one, and this one in one. I can do that in one command. Because normally I want to use the first K principal components, say 5 principal components, then restore the R matrix, the G matrix, and the B matrix, and then compress that into a picture. But instead of writing that 3 times, I'm going to use the sApply function. But first, I'm going to store all my PCAs in a list. And then I'm going to use the sApply function. I'm going to use the sApply function on PCA. So on this list, I have my R, my G, and my B matrix. I'm using the extract function. K is equal to J, so I'm going to use the sApply function for M, meaning that I first use extract where M is equal to this one, then is M equal to this one, then M is equal to this one. But the K, the second argument, is always equal to J, where J is 5, 10, 100 or 500. And then I make sure that everything is in an array, because otherwise the JPEG function of my library that I use here cannot store the data. So this is my compressed photo, right? I use only a small number of principal components, and then I'm going to extract the original values by inverting the rotation matrix. Then I apply the write JPEG function that will store my approximate photo in the same folder as where I have this this R script. So this is the one that I want to store, and I have to give it a name, and I give the name Quentin Juno. So each photo I store has a name Quentin Juno, but I have to I want in the title of the picture that I store, I want to put whether I use 5, 10, 100 or 500. So I'm going to call it Quentin Uno. Then I put the number of components and then I make sure that it ends on GPG for the picture. So we can have a look in our folder. So I have my folder here where this is the original picture. And then you see here that R added 4 pictures. These are the pictures that I made using the PCA with 5 principal components, 10, 100 and 500. And the main takeaway here is that with only 500 principal components, which is less than half of the principal components you need to restore the full picture, we actually get a very good approximation of the original picture. So whereas the original data, the original picture, has 1000 plus variables, I can reduce that number to 500 and still have a good representation of the picture. Thank you very much.